Good morning, everyone. It's nice to be here, and I'm honored to be invited to give a talk in SEMICON Taiwan. And actually, this is my first time to give a speech because in SEMICON Taiwan, because I am an AI researcher and engineer in the AI world, and for semiconductor, this is my very new and fresh experience for me. So I'm glad to be here, and today my talk is breaking boundaries, how to use AI to power the design of compound semiconductor design, and to enhance the efficiency during the design process. So my talk is kind of different from every talk that before me. So before me, the talk looks like how to use compound semiconductor to empower AI era, right? But my talk is kind of the other way around. We are thinking about how to use AI technology to increase and enhance the design process so that we can enhance the power IC quality, so that we can make this design process go more faster and smoother. So this is outline of my talk. I will talk about鴻海's AI strategy and challenge in industrial manufacturing, and AI for TK semiconductor design optimization. And finally, I will do a comparison between different methods. So now first, let's look at the full stack of the AI industry. So yes, indeed, I agree that semiconductor technology is very important and is fundamental for our AI technology. So for me, all of most of my life are spending on this domain, including how to build foundation model, how to build AI model, and let this model to have a lot of different functions, like this model can do amazing things: dialogue, translation, summarization, reasoning, VQA, and we can build AI application on top of this. Like we can, now with the capability of the foundation model, we can do companion robot, AI coder, AI writer, AI search engine, and all of these things. But we need a very strong foundation of the hardware side. So for the hardware side, we need GPU, and we need high-speed interconnection between GPU in order to fulfill the need of the computation for the AI model. And also for the computing system, we need to have a good cloud server, edge node, and user device. And all of these will be the indispensable foundation to help us to build useful and AI applications. So in FastCom, we have a lot of business doing fundamental modules like IC, component, and module and systems. So in this new AI era, we are thinking about whether we can go a step further and lift us to the next level. We would like to leverage our existing power capability and move us to the new level as a platform builder. So in this new AI era, we hope that we can build new AI platform. Specifically, we want to build a platform for smart manufacturing, smart EV, and smart city, and to help our ecosystem partner and customers to build their own application. However, semiconductor technology is fundamental for all of this. Take smart EV as an example. In order for us to have good and safe EV, we need good and reliable power IC. And one of the important characteristics of reliable IC is high breakdown voltage. And good design parameter with good manufacturing process will generate desirable power IC with high breakdown voltage. However, the traditional workflow for generating good design parameter for IC relies on experienced engineer, and they have to guess what is the good initial parameter and fix it with trial error fashion. This is very time consuming and tedious. So, and also when the engineer are working very hard to design the parameters, his boss may ask him, can you do it faster? Can you do it better? Or can you do it with lower cost? So this hard-working engineer will spend more time working and lose the work and life balance. So his life will be miserable. Yeah, so this is why we need to introduce generative AI. Here is generative AI comes to rescue. So the power of AI is driving revolution of industrial design and manufacturing toward more efficient and intelligent direction. However, the benefits of AI technology in industrial design and manufacturing often require in-depth interdisciplinary collaboration, which is usually difficult because two parties speak quite different language. So what we just heard for the previous speaker, he talked about GAN, right? In our world, in AI, we also have GAN, but they mean totally different things. So GAN in semiconductor means gallium nitride, right? But in our world, we also have GAN, and this is a very important deep learning model that we use for a lot of different tasks. So we speak differently and we think differently. So how to collaborate these two kinds of people and do things together and have a really workable solution, it's really quite difficult. But today I want to share with you guys a successful story, which is AI for TK, Semiconductor Design Optimization, happening in鴻海Research Institute. And this is the collaboration between AI Research Center, led by me, and the Semiconductor Research Center, led by Professor Guo. Yeah, so now let's go into the detail about our technology. So here is the overall flow chart of design process for semiconductor device. There are totally mainly four stages here. First, we need to select good design parameter for this device. And second, we need to go to the simulation software to run simulation to see if the simulation result meets our requirement. I want to emphasize the importance of this second stage because simulation tool like TK play a crucial role in the semiconductor design process, especially in the stage of adjusting design parameter to obtain good electrical property. And if the simulation result is not good enough, maybe we need to go back to the first stage to redo the parameter selection. And after you have finished the simulation stage, we move to the third stage and we start to fabricate the device. And after it is done, we do device testing and analysis to see the electrical property of the device meet the requirement. And if it does, then we are happy and the job is done. However, if it is not, then our miserable engineer appear again and he needs to repeat this process again and do it again and again until we got our device correctly manufactured. So how can AI help in this process? So we can simplify the previous process into a circle process like this. First, we need to do parameter selection, and then we input this selected parameter to TK to do simulation. And then, after we have output from TK, we measure the performance. And then we fine-tune the parameter if the performance is not good. And during this circular process, the running time for TK is very long. Usually it takes 4 to 8 hours per set of data. So we can use AI for both TK acceleration and parameter selection. So by using AI to replace this hardworking engineer, what we can do is we can train an AI model to simulate the behavior of TK. And by doing this, we can speed up the TK simulation to a very great degree. And also we can use some optimization method provided by AI algorithm to help us better select parameters. So here we use a design parameter of silicon carbide VD MOSFET with breakdown voltage of 1.7 kilovolts as our starting point. So silicon carbide VD MOSFET is a semiconductor device with high voltage resistance, high frequency, and high temperature operation capability, suitable for high voltage power electronic applications. So there is a lot of design parameters in the silicon carbide MOSFET as listed in the pictures here. And among them, we choose 3 sets of parameters, including number of guide rings, dose concentration, and energy combination. As we were told by the semiconductor people that these are the most important design parameters. If it is not the case, please blame Dr. Guo. Because this is what they told us. Okay, and the objective of this work is we starting from this design parameter, and we want to adjust these 3 parameters so that the final breakdown voltage of the device can be increased to 2.7 kilovolts. Okay, so before we go into the detail of the AI model, I want to see this problem from a new perspective and let you know that this is not as easy as a classical machine learning problem. I think we should call it reverse prediction. So this is the process of the classical machine learning. So for classical machine learning, we gather data and we have a trained AI model, and we input this data into this model, and we have the classification result or prediction result. So in this classical flow of machine learning, the data is the input and prediction is the output. But in our case, which is the design parameter optimization, again, we will have AI model trained trained using our past history of the data. And but in this time, we have a target breakdown voltage, and this is our final goal. But we don't know what's the input data should we use. So in this problem, we have AI model, and we have the target breakdown voltage. And by using these two, we want to predict what is the good design parameter that when we use it to feed into the model, we can get the correct target breakdown voltage. So from the AI model perspective, again, the red part is the input and the green part is the output. But from the system perspective, the green part is input and our output is the red part. So this is quite different from what we learn or what we usually do in classical machine learning. So we call it reverse prediction. So we utilize the following machine learning method to achieve reverse prediction, assisting in industrial design parameter optimization. These two methods is surrogate model and conditional VAE. First, the surrogate model, it is a predictive model that simulates complex systems with few computational resources, saving time to TK simulation. So the first step is we want to train a model, machine learning model or deep learning model based on our data set. So we accumulate the data from the past history, accumulate a lot of TK input and output data, and use all of this accumulated data, we train a machine learning model. so that this model will simulate the behavior of the TK software. And after the surrogate model is well trained, it can be used to fine-tune the design parameter in the optimization process. So the whole process is shown on the bottom. So first we define the parameter search space, and then we define the loss function, and then we sample a set of parameter from the search space, and we input the design parameter into surrogate model instead of TK. So in this step, we skip TK and we use surrogate model to replace that. And then surrogate model will output the predictive breakdown voltage. And then we calculate whether how much the loss is, and then if we are not satisfied with the current breakdown voltage, we will go back to do the sampling again. And this process will go iteratively until we have a feasible and satisfied solution. So here is the experimental result for surrogate model. So in this experiment, we simplify our problem to use just two sets of parameters, dose and energy. And we train a surrogate model and follow the working flow in the previous page until we find the optimal set of parameters. And the third column here shows the 5 sets of results that we get from the workflow. But finally, in order to verify the parameter, we run TK for each set of the result. And due to the training error, the output of the surrogate model will not be exactly the same as the TK output. There must exist some error. So you can see that this value and this value is not necessarily the same. And after we use TK for verification, we can see that we got one solution, which is the fourth one, which satisfies our design requirement. Okay, so that's the first method. And the second method is called conditional VAE. So before we go into this method, I need to do some introduction about the foundation of this method. So let's begin from the autoencoder, AE. So autoencoder is a deep learning model which trying to learn how to do data compression in a very efficient way. So an autoencoder consists of two parts, encoder parts and decoder parts. And during the training stage, encoder learns how to compress the input data X into another vector Z in a very much lower dimension. So the data X is the data that you are interested in. It can be anything, like it can be image, video, speech, or anything that you are interested in. And the goal of this encoder is trying to do a mathematical transformation to transform your input data into another vector. But the dimension or size of this vector is much smaller than the original data X. So we call this variable Z as compressed representation because it's trying to compress your data into a smaller size vector. And at the same time, the decoder is trained to do the inverse operation with respect to the encoder. So the decoder is trying to convert Z back into the original input X. So the output X prime should be as close as to X. So during the training, ideally we would like to see X equal to X prime. So this is the objective function that we use to train the autoencoder. And after we have autoencoder, some clever scholar come up with a new idea called variational autoencoder. So for this variational autoencoder, it's trying to put another constraint to constrain the distribution of the Z vector to fall within the unit Gaussian distribution. So after we put this constraint into the whole training process, the Z, the compressed representation Z, will stay in a standard normal distribution. And the benefit of doing this is that if it's resigned in a null distribution, then we can easily resample it from this distribution and to generate new data from this VAE model. Okay, so now let's talk about our real method. This is conditional VAE. So in this method, we modify the VAE model so that in the encoder part, it does not simply output the compressed representation Z, but it also output another variable, Y hat. And we want to make Y hat to be equal to our target BV value during the training time. And we also modify the decoder and so that the input of the decoder is not Z, but it's the concatenation between the Z and Y. So the new input feeding into a decoder, and it will output X hat. And again, we want to constrain that X and X hat should be as similar as possible. And also want to constrain that Y should be equal to the target BV value during the training stage. And after this CVAE is trained, how do we use that during the inference stage? The way we use that is to first use the decoder part. So we sample one solution from the standard normal distribution and concatenate it with our target BV, so that we can pass through the decoder. We can have an initial suggestion about our parameter. And secondly, we use the encoder. We put this value suggested parameter into the encoder, and it will give a predicted breakdown voltage. And if this breakdown voltage is different than our requirement, then we can compute their difference. And by doing the gradient descent and back propagation, we can back propagate the difference to the X. And then we can adjust the X through the back propagation. And by this way, we can adjust the parameter and get a new parameter. So here is the experimental result for CVAE. So in this experiment, we set the target BV value to be 2,710, a little bit higher than 2.7 kilovolt. And the parameter we want to fine tune is Gaussian rate number, dose, and energy. And by using our method, we have the initial value of BV of this, and after using TK to verify, we get this value. And this value is a little bit lower than our target value. So we do the back propagation that I said in the previous slides, and we do different kind of back propagation. And among all of these 4 different back propagation, we get one single solution which satisfies our design requirement. So this is how we do it with CVAE method. Okay, let me conclude with the comparison of these two methods. For the surrogate model, it's easier to understand and needs fewer training data. This is the advantage of this method. And also, the downside of this method is hard to find solution for multiple targets and needs many iterations for a single solution. And the advantage of CVAE is easier to converge to the solution and easy to extend to advanced model, which are able to predict multiple target values. But the downside is it needs more training data to train this model because it is a more delicate model. So we hope that we can stand on top of this good result and develop even more advanced deep learning method for parameter selection and suggestion. And we will share more of our results in the future if we have new achievement and discovery to share. Thank you.
Okay, so now we are open for question. Yes.
Thank you very much for the very nice sharing. Especially, it's very interesting to know that silicon carbide power device can be optimized by using the machine learning-based approach. Well, as far as I know, right now the machine learning-based approach can predict the results if the results are inside the training data set, in the range of the results are inside the range of the training data set. But how about, if possible, to predict the result outside the training data set?
Yeah, this is a very good question. Actually, this is also one of the difficulties that we met during our research. And I think if we have more training data, that means if we sample more densely in our TK simulation, then I think it's still possible to help us to predict value that beyond our sampling scope. This is why AI and deep learning is so powerful, because it can generalize to the problem that it didn't train before. So this is why everybody is using AI now, because it has this generalization capability. And I think if we do things right, in the near future, we should be able to extend our method to achieve this.
Thank you very much.
Indeed, this very interesting talk for that. I just wondering, how do you compare so-called the AI model to people use more like empirical data collection, and then to create a neural network to retrieve the all the information?
Mm-hmm.
And would that be any analysis? I mean, analogies between these two, or do you think it is different?
Yeah, I think the method you mentioned belongs to our first method, surrogate model, because the surrogate model can be any kind of machine learning model. It can be like what you mentioned, artificial neural network, ANN, or it can be deep learning, or it can be classical machine learning, like decision tree, random forest, support vector machine. Yeah, I think it belongs to our surrogate model method.
Okay, so let's thank the speaker again. Thank you, and very well presented.